Okay, so let's say I have some function, p of x is equal to ax to the seventh power plus bx to the sixth power plus cx to the fifth power plus dx to the fourth power plus ex to the third power plus fx to the second power plus gx plus h. So we have some polynomial. What's the degree of this polynomial? What's the degree of this polynomial? 7, good. The degree of the polynomial is always our biggest exponent once it's all multiplied out. The degree of this polynomial is 7. Okay, how many roots are we going to have, or how many zeros, or if we were going to solve for x, how many solutions would this have to have? Okay, algebra 2 question. So basically, you have as many roots as your highest degree. So basically, if I have, that's why when you have like x squared equals 4, your highest degree is 2, which means you're going to have 2 solutions. So if my highest degree is 7, what does that mean? We're going to have 7 solutions. If my highest degree is 10, that means I'm going to have 10 solutions. So here, our degree of the polynomial, our highest degree is 7. That means we're going to have 7 solutions. But it does not necessarily mean that they're going to be real number solutions, right? It doesn't necessarily even mean that there'll be rational solutions. So it just means I'm going to have 7 solutions. So they could be irrational, they could be rational, or they could even be imaginary. Right? It just means that when I solve for x, I'll have 7 answers, but it doesn't mean that there'll be real number solutions. Hey, when I ask you to find the roots, or I ask you to find the zeros, visually, what are we looking for? When I'm asking you to find the roots or find the zeros, what are we looking for visually in the graph? Excellent. It's where the line crosses the x-axis. So if I gave you something, you don't have to draw this, but if I gave you something, why'd that happen? If I gave you something like this and I asked you to find the zeros or the roots or the solutions, do we agree those dots would be our zeros? Okay. Now let's talk about when we're solving something and it's a little bit more complex, when we're bringing into the imaginary world. So if I have x squared plus 2 equals 0, right? And I want to solve for this. Well, wouldn't we subtract that 2 to the other side? And then to undo a square, what do we have to take? The square root. To undo a square, we have to take the square root. Are we allowed to have a negative under the radical? No, that immediately makes it what? Imaginary. But the minute we take the square root, how many solutions do I now have? 2. Don't we have to account for plus or minus? So we'd have plus or minus I root 2. And how's the only way we get an imaginary number? When you take the square root of a negative number, right? So what does that tell us? Every imaginary number has to come in how many? 2. They have to come in pairs. Every imaginary number has to come in pairs. Why am I doing all this? Because if we know the idea that imaginary numbers have to come in pairs, we could sort of figure out what our options for imaginary versus real. Okay, Ken, is it possible that I have this polynomial, ax squared plus bx plus cx, blah, 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 is it possible for me to have 7 real roots? Could that happen? Absolutely. If I have 7 real roots and the degree of the polynomial is 7, how many imaginary roots would I have? 0, right? Because all 7 are already accounted for as real. Okay, let's say is it possible for me to have 6 real roots? If I have 6 real roots, how many roots do I need altogether? 7. I need 7 roots altogether. If I have 6 real roots, is it possible to have just one imaginary or complex root? No. Why is that not possible? You need the pairs, exactly. So to have 6 real roots and one complex or imaginary root is not possible. Complex comes in pairs. All right, could I have 5 real roots and 2 imaginary? Is that possible? Absolutely, that's possible. Let's keep going. Can we do 4 real and 3 imaginary? No, because again, complex comes in pairs. Do we get the gist? Do I need to keep going with this? All right, good. Moral of the story, complex comes in pairs. All right, let's talk about the rational root theorem. So the rational root theorem is a way to get a list of all possible rational roots. So it's a way to get a list of all possible rational roots. Now keep in mind, rational is very specific. Rational is very specific. What is not included in this list? Imaginary is not included in this list, but what else is not included in this list? That still falls under real. Fractions and decimals, as long as they're repeating, non-repeating or repeating in a pattern, fall under rational. So fractions and decimals will fall under this list. Dylan? Nope, negatives fall under rational. Irrational, right? Irrational. Like, numbers that repeat in a decimal, numbers that repeat in that go on in a decimal that don't have a pattern, like the square root of 2. The square root of 2 is a real number, right? It's not imaginary, but it's not rational because that decimal just keeps going and going and going and no pattern, right? So this list only gives us rational roots, meaning positive numbers, negative numbers, decimals that don't repeat or repeat in a pattern, and fractions. That's what this gives us. So anything that's irrational or anything that's imaginary, this does not give us. All right, let's keep going. So how does this work? Let's say I gave you an example and I told you list all possible rational roots. Of 2x to the third minus 5x squared minus x plus 6. The way we're going to do this is we are going to take factors of the constant, which we call P, over the factors of the leading coefficient, which we call Q. So when I say, P over Q, I'm saying factors of the constant over factors of the leading coefficient. Write it down and I will show you. Perry, could we take our AirPods out? Anybody else that has AirPods in, please take them out. Thank you. Okay, so we're looking for P over Q. Our constant is P, our leading coefficient is Q. So I'm going to take factors of 6. Well, what are factors of 6? We can do plus minus 1 and plus minus 6, right? 1 times 6 are factors, but we have to count for positives and negatives. And then we could do plus minus 2 and plus minus 3. Are there any other factors of 6? No. All right, and now we're going to do that over the factors of the leading coefficient. So the only factors of 2 are plus minus 1 and plus minus 2. Now what we do is we pair every numerator with every denominator to get our running list. Leave your hand up or no? Okay, so our running list is going to be plus minus 1 over 1, right? Pair the top with the bottom. But then it's also going to be plus minus 1 over 2. Then it's going to be, now we're done with 1. Now we go on to 2. Then it's going to be plus minus 2 over 1. But what's 2 over 1? Just 2. And then it's going to be plus minus 2 over 2. But what's 2 over 2? 1. Isn't 1 already in our list? So we're not going to write it again. Then we move on to 3. We're going to do plus minus 3 over 1, which is just 3, plus minus 3. Then we're going to do plus minus 3 over 2. And we move on to 6. We're going to have plus minus 6. But then 6 over 2, isn't that 3? That's already there, so we're not going to write it again. This is the list of all possible rational roots. Mm-hmm.
So how come, if you said the amount of answers there would be is like the exponent on the leading coefficient, why is it that there's 6 here, but...
So I'm so happy you asked. So these are not the roots. What is the word? These are possible rational roots, which means if there is a rational root, and there might not be any rational roots, if there's a rational root, it will be in this list. But that doesn't mean all of these rational roots are the roots. Just if there was a rational root, it would be one of these. All right, let's do a problem. So I want us to use the rational root theorem to list the possible rational roots, then find the factors. And our equation is going to be 2x cubed plus 3x squared minus 8x plus 3 equals 0. So our first step is going to be find the possible rational roots, which we call P over Q. So I need factors of my constant, P, over factors of my leading coefficient, which is Q. So factors of my constant are going to be plus minus 1, plus minus 3. Factors of my leading coefficient are going to be plus minus 1, plus minus 2. Now let's list. So our options are plus minus 1, plus minus a half, plus minus 3, plus minus 3 halves. Okay, so now this is the transition. How are we going to use this to help us find the possible rational roots? Well, what we're going to do now is use synthetic substitution. Use synthetic substitution to see which will give a remainder of 0. So now remember, guys, this is already in the format as x equals, right? X equals plus or minus 1. X equals plus or minus a half. X equals plus or minus 3. X equals plus or minus 3 halves. So we're not changing the sign. Because normally when we're doing synthetic division, if the factor was x minus 1, we'd say, okay, well, x equals 1, right? Well, this is already x equals format. So we're not changing the sign. We're just going to plug it right in. So now I'm going, I don't know, where do you guys want to start? It's tedious. There's no shortcut here. It's all going to just be tedious until we use the calculator. Then it will be nice and easy and short. But right now, for the purpose of today until tomorrow when we use the calculator, it will just be tedious. So you tell me, where do you want to start? Any guesses? 1. Let's start with 1. So we're going to put positive 1 in our box. And then we list out our leading coefficients, 2, 3, negative 8, 3. I didn't need to put a 0 for anything because every exponent's accounted for. Bring down that 2. 2 times 1 is 2. 3 plus 2 is 5. 5 times 1 is 5. Negative 8 plus 5 is a negative 3. Negative 3 times 1 is a negative 3. 3 plus negative 3 is 0. When your first guess works, you're so lucky. Okay, so now this is a remainder of 0. What does that mean? It means it's a factor. But remember, this was x equals 1, right? So x equals 1 is not a factor. We have to go back to the factor. How do we change this back into a factor? It becomes x minus 1, right? You just set it back equal to 0 by subtracting that 1. So we have one factor, which is x minus 1. So now I'm going to put a star. Continue to use synthetic substitution until you have a degree of 2, then factor or use quadratic. quadratic formula. Oh, degree of 2. Once we do synthetic division or substitution once, how do we know the degree of our new polynomial? What is it?
One less.
One less than what we started with. So what did we start with? We started with x cubed, right? So what is this new one going to be? X squared. So this is going to be 2x squared plus 5x minus 3. Are we down to a degree of 2? Yeah, our biggest exponent is 2, right? Are we down to a degree of 2? Yeah. So I wouldn't waste your time by doing more guess and check. Now I would take this and I would either factor it if we can or use the quadratic formula. So let's go. So I know one factor is x minus 1. And then we have 2x squared plus 5x minus 3. We're going to factor this. So we have x minus 1. And then if we factor this, we are going to get 2x minus 1 and x minus 3. Nope, plus 3. There we go. Have we successfully brought it down to all its factors? Yes, there's nothing else that can be factored, so you know you're done. So this is the factored form. These are the factors.
So once you find the remainder of 0, there's only going to be 1. Like if we were to plug it into the other 3.
No, so you would have had more. So there's 3 rational roots here. Look. So this first root was 1, which is the one we chose. This one is a half, and this one is -3. So if you continued to use synthetic substitution, you would have gotten all 3 of these. So just to show you, these are all rational roots, and they were all in our list, right? 1 was in our list. A half was in our list. 3 was in our list. So if there was a possible rational root, it was in the list. So let's say you did 3 first instead of 1, it would have worked out. If you would have done -2, would it have worked out? No, then you would have had to guess a different number to try. And like I said, there's no shortcutting guessing. You sort of just, you and your luck. Yes.
And then is it just for this problem, the degree of 2, or is it for every problem?
Every problem. You keep using synthetic substitution until you get it down to a degree of 2, and then you either factor or use the quadratic formula.
If it's like 2x to the 4th at first, then
you do it twice. Yep, we're going to do more. Okay, so now there's something we also have to consider called a double root. Does anybody know what I mean when I say a double root? Okay, so a double root is something like, for example, generally if we have a parabola, we have something like this, right? Where here's a root and here's a root. Do we agree? And a parabola is always x squared, right? It's a quadratic, a parabola, it's always x squared. But sometimes it doesn't go through. Sometimes it comes down, it hits that root, and then what happens? It bounces back up. So in this scenario, even though the equation for this is y equals x squared, that's what this would look like, the equation. It's saying I have a degree of 2, so how many solutions do I need? I need 2 solutions. But what has happened is we didn't go through the point. We hit one root and bounced back up, which is called a double root, meaning that root counts twice. That root counts twice. So it's 0 and then another 0. Another idea of that is something like x minus 2 squared, right? That will be a double root because it's x equals 2 and then x equals 2 again. Those are double roots. All right, so we have to check for double roots when we're doing this. So let's say I ask you to find all roots. So now I want the roots, not the factor. Find all roots. And I'm going to have x to the fourth plus 5x cubed plus 15x squared plus 19x plus 8 equals 0. Before I find all the roots, where do you think I'm going to start off with? Where should we start? Leah? P over Q. We want the possible rational roots. So we're going to find P over Q. Factors of the constant, here's our P, over factors of our leading coefficient, where here is 1, that's Q. So we're going to do plus minus 1, plus minus 8, plus minus 2, plus minus 4. What's really nice about having a leading coefficient of 1? We're not dealing with any fractions, right? It's just plus minus 1. So our possible rational roots are going to be plus minus 1, plus minus 2, plus minus 4, plus minus 8. All right, next up, what do I now do that I have my list of possible rational roots? We have to start testing to see which ones are actual roots. So how are we going to test to see which ones are actual roots? Evie? Good, synthetic substitution. All right, let's start with negative 1. So when we list out our leading coefficients, we are 1, 5, 15, 19, and 8. So now I was at x to the fourth power. What did I say to bring it down to? To a degree of what? 2. So how many times do I have to successfully do synthetic substitution? Twice to get it down to a degree of 2. So this is negative 1. And now, do you see how all my leading coefficients are positive? In order to get a 0 at the end, it's obviously not going to be a positive in the box, right? Because if it's a positive in the box, it's just going to keep getting bigger and bigger and bigger. I know it has to be a negative. So that takes away all my only positive options. So let's go here, bring down the 1. 1 times negative 1 is negative 1. 5 plus negative 1 is 4. 4 times negative 1 is negative 4. 15 minus 4 is 11. 11 times negative 1 is negative 11. 19 minus 11 is 8. 8 times negative 1 is negative 8. 8 minus 8 is 0. Did this work out as a factor? Or a root, I should say. Yes. Now this is down to a degree of 3. So this is x cubed plus 4x plus 4x squared plus 11x plus 8. I'm going to check for double root. The way I'm going to check for double root is now I'm going to take this and put in negative 1 again. So I'm going to take this. This is how we check for double root. Take that and put in negative 1 again. So now we're 1, 4, 11, 8. 1 times negative 1 is negative 1. 4 minus 1 is 3. 3 times negative 1 is negative 3. 8 minus 3, 11 minus 3 is 8. 8 times negative 1 is negative 8. Did it work? Yeah, so that means there was a double root at x equals 1. So what does that mean? It bounced back up, right? It hit -1, and instead of going through -1, it bounced back up off of -1. So now what are we down to? A degree of 2. So now we are x squared plus 3x plus 8 equals 0. Can I factor this? You cannot factor this. So what did I say to do if you can't factor it? Factor it or the quadratic. And remember, the quadratic is x equals -b plus or minus the root of b squared minus 4ac all over 2a. So we are -3 plus or minus 9 minus 4 times 1 times 8 all over 2. So we are x equals -3 plus or minus the root of 9 minus 32 all over 2. So we're going to have the root of -23. That's all over 2. What is the root of -23? You can't leave the negative in there. Never allowed to leave the negative. So what should we do? Pull out an I. Yep, we need to pull out an I. So x will equal -3 plus or minus I root 23 over 2. How many roots is this? How many roots is this? 2. Why 2? Because we have 3 plus I root 23, but then we also have 3 minus I root 23. So this is 2 roots. And then we had x equals -1, which was, I'm going to say dr, which is a double root. How many roots is that considered altogether then? 4 roots. Did we need 4 roots? Yes. These are our roots. What's up?
How is it 4? So the quadratic is 2.
Yep.
And then the x equals, okay.
The double root counts as 2.
Okay. But also,
yes.
Didn't we say like if it's in synthetic and it's -1, then you switch it to like a +1?
No, so that's when we're doing synthetic division. So when we're doing synthetic division, I'm giving you the factor. So let's say, don't write this down, but when we were using synthetic division, let's say it was x squared plus 5x plus 6, divided by x minus 1. Mm-hmm. So what we were doing is we were taking that x minus 1 and then solving it, saying x equals 1. So what's happening now is I'm already giving it to you in that x equals format.
Okay, because I was just like looking at number 1 because we switched it at some point.
I don't think so. Let's go back.
It was
Oh, that's when we were asking for the factors. So there's a difference when I ask for the factors versus the roots. The roots are the actual point that it crosses. The factors are what's multiplying. So that's when you take that root and you go back to 0. So it all depends on what I'm asking for. Do you see the difference? Okay. Can I go on to the next one? Okay, do you guys want to try one on your own? Try this on your own. I want you to find the factors. Find the factors. If you need help, raise your hand. I will come help you. Also, just point out, I'm missing an exponent. I am missing an exponent there. So just to point that out when you're doing your synthetic substitution. So once we're allowed to use the calculators tomorrow, it will take the whole guessing part out. Once we're allowed to use the calculators tomorrow, it will take the whole guessing part of this out.
For the P,
Mm-hmm.
did you have like one of the factors of negative 2 just be like,
No, just you don't put the
oh,
sign.
just a 2?
Just two. Don't put the signs in them. So we're missing two exponents. We're missing the exponent of 3 and the exponent of 1. If you don't know how to bring the roots back to factors, just stop at the roots at least, and then I'll show you how to bring it back to factors. So if you don't know how to bring the roots back to factors, just stop at the roots, and then I'll show you how to bring it back to factors. So I will tell you 1 and negative 1 should work. 1 and negative 1 should work. Both 1 and negative 1 should work. Like I said, I don't really mind telling you this because tomorrow we'll be able to look at the graph and sort of figure it out on our own, which ones should work. What to go?
It's like I understand that you can pick this one, but this for this one.
Mhm.
This one, this one.
But that's only 2 factors, right? You're
Right.
saying you don't know how to get the other factors, right?
Unless they're just
No. So what you're going to do is once you get it down to x, is this the second one you did? Okay, so then this is going to be x squared, right? Plus 2 equals 0, and then you solve. So you always get it down and then change that last one into a quadratic and solve it. No, x squared, that's 0x plus 2. So do you really need the 0x? So it's just going to be x squared plus 2 equals 0, and now you solve. You're welcome. Who wants another minute? Okay. We don't have another minute. Sorry. Let's go through this real quick. So I told you that 1 and negative 1 work. So we know x equals 1, x equals negative 1. I did negative 1 second. So when I got my last thing, it was 1, 0, 2, 0. Which brings us to an x squared plus 0x plus 2, right? Isn't that the quadratic that you're left with? I'm going to set it equal to 0, and then we solve. So we're going to have x squared equals negative 2. square root both sides. We get x equals plus or minus I root 2. Do we agree? Okay, so my roots are x equals 1, x equals negative 1, x equals I root 2, and x equals negative I root 2. These are the roots. These are not the factors. How do we change the roots back into the factors? Set it back equal to 0. So what does that mean? Minus 1. So it's x minus 1. That's one factor. Add 1 here. So it's x plus 1 is another factor. Subtract I root 2. So it's x minus I root 2 is a third factor. Add I root 2. So it's x plus I root 2 is our fourth. This is where you're at. All right, this is where we're going to stop. You do have homework tonight. Sorry. Oh, look at that.